Good afternoon, everybody. Welcome to the PostgresWorld Webinar Series. I am a co-chair of the conference series, as well as the CEO of Command Prompt Inc., one of the oldest Postgres support providers in existence, as well as the oldest in North America. If you have any Postgres questions or would like to have a chat, please email me directly at amanda@commandprompt.com or feel free to connect on LinkedIn. Today, I have the privilege of introducing a genuine character on our Command Prompt team, full of delight and lots of knowledge, Greg Dostatni. He will be presenting proper Postgres parameters to prevent poor performance. And great job, Greg, on getting so many P's in there. So without further ado, please, everybody, give a warm welcome to Greg, and I hope you have a great webinar. I look forward to connecting with you later on.
Thank you, Amanda. So that was, I've got to admit that the title of the presentation came first. The content, I had to come up with something to fit the title because it's awesome. So this is proper Postgres parameters to prevent poor performance. It's a beginner-friendly talk where we're going to discuss some of the core pieces of Postgres, how they fit together, and which parameters allow you to adapt your system to your needs. It doesn't go too much into the depth of like all the different kinds of parameters you can. We just focus on making the big pieces of Postgres work well together with the environment. So my name is Greg Dostatni. I'm a DBA. So let's start with what's the goal, right? The goal is, as I said, to make this presentation approachable, beginner-friendly. The goal is also to understand the trade-offs. It's not always the easy thing of saying that you need to set this parameter to get better performance. Everything inside of computers in general is all about trade-offs, and what we all need to have is understanding of what happens when we change this versus that, and how do we adapt to the workload. The other aspect which kind of got me going on this talk is just the sheer number of parameters which is available in Postgres. In version 9.6, we had about 260 different parameters available. Version 17, we're approaching 380. So there is a lot of knobs that we can turn and adjust and change, and they all do something. Knowing what to do is sometimes a challenge, and knowing what the effect it's going to have is difficult. So this talk will help create kind of like a roadmap of where of what you might want to change, and will help you get the big pieces into a good shape before you start kind of optimizing down some of the more let's just say less commonly changed parameters. So before we get into the parameters we want to change, we need to talk a little bit about the data and the workload that is that your servers are running. So data. What's important about data? The size of each row, the size of the total amount of data in a database makes a huge difference. How wide are each rows? The size of each row makes a big difference. How many rows in a table And what is the complexity of the query? So to give an example, having a very wide table where each row has, let's say, a kilobyte of data, the way you optimize that will be different than if you have, let's say, 50 let's say 50 bytes per row and a lot more data. Let's say 100 let's say 100 million rows in a table. Doing many complex joins between large tables will also change how your system needs to behave, how it needs to pull data out of the storage, and how much data it needs to keep in a cache in order to make the joins efficient. In order, how much data it needs to set aside for the cache to make sure that all the indexes are stored in memory, if possible, so that it can look up whatever you're looking for efficiently. So the data describes what you have and how you're using it. The other big piece of that is the workload. That's typically is described in a couple of industry standard terms like OLTP, online transaction processing, OLAP, online analytics, data warehouse. So in my mind, those typically, the big difference here is how much data is processed by the average query. So OLTP would process generally a small amount of data. You would expect the query to return in less than a second. You just process, let's say, this one user's record. You update their message counter or something like that. Those are typically very quick queries. Process a small amount of data and do some updates, retrieve some information, display something on the screen, display a widget on the screen. Analytics is medium range. Maybe you run some kind of a quick report, provide the daily average of some kind of processing report. Analytics queries would generally run, I don't know, 20 seconds maximum. They process kind of a medium amount of data, gets the result, and something that's near real time, maybe not quite real time. And data warehouse type workloads, they could run for hours, generate deep reports, and churn through like years worth of data. So the length of the query, of your average query, obviously changes. It changes how you optimize how much cache you need. The most difficult workload possible is where you're trying to support all three types of workloads at the same time. So when you're trying to optimize both for queries that, excuse me, both for queries that are expected to run for hours, and also a large volume of sub-second queries that have to happen at the same time. Those kinds of trade-offs are extremely difficult to take into account. Another little sidetrack is, let's talk about what happens when Postgres needs to retrieve data from disk. So the data obviously lives on disk in some kind of a storage. It may be NVMe, maybe fiber attached, maybe network attached storage. It has to live somewhere. So retrieving it so you have a query and it requests a block of data from disk. So the request goes all the way down to the disk layer, and the appropriate block is retrieved. The operating system will then load it into cache, and it's available at that level as long as it stays in a cache. So having it in a cache means that you no longer need to retrieve it from disk. Sorry, you know what? Let's go back a little bit. I think I fumbled the slide. Let's go backwards. That might be easier to understand. You have a query that requires that needs to retrieve some data. The first place that it looks for is in a work mem. So work mem is an area of memory that is allocated to your existing connection. It is a work mem by itself. It's a maximum amount of memory that Postgres will allocate to that connection. So it's a limit. The actual amount allocated depends on how much data this specific query needs to retrieve. So at first, the query will look in its work mem to see if the data is available there. Maybe it's part of a longer transaction. Maybe this data was retrieved previously, so it may be just available directly in its local memory cache. If it's not available in its work mem, then the next place that it'll start looking for it is in a shared buffers. Shared buffers is an area of memory that is allocated to the Postgres server as a whole. The main Postgres process. It's available through an inter-process communication call. So it's still relatively fast. It's still in memory. There's a little bit of overhead of calling the main process. There's a little bit of logging involved, but it happens largely at memory speeds. And if that data was, for example, retrieved by a different query, by a different connection recently, then it can very well be in shared buffers. If it's not available in shared buffers, then the Postgres will make a request to the operating system to retrieve this data, which again could be in file cache, like I described just previously, if it was loaded from disk just recently. And finally, as the last step, it'll retrieve the data from disk, where the top three layers, they happen in memory with various number of overhead related to locking or system calls. The last happens on disk. And retrieving data from disk is generally thousands of times slower than accessing it from memory. So the closer we have the data that this query needs to its memory, its local cache, the faster things go. Now, what happens when Postgres writes data? And this process is quite interesting as well. Retrieving data is by comparison easy because the data is on disk. You don't really need to think about too much. You just grab it from the next place that it's available. Writing data, well, you have a query that updates a tuple on a table. So the new tuple gets created. Postgres doesn't really change things. It always creates a new version of the row and puts it in. That's a simplification, but basically MVCC means that you don't change what exists. You just create a new version of it, and it kind of overshadows the old one. So the new tuple gets created. There have to be some integrity checks because it's a relational database. So we need to make sure that foreign key references get satisfied. All the other constraint checks are done. Then the wall entry is built and it's created to the wall buffers. So wall is the write-ahead log. It builds the data page that was just modified and puts it in the wall buffers to be written to disk. So then the wall record gets sent to disk. At that point, the transaction is considered safe and committed because the data can be replayed from the wall record. So that's asset compliance. The transaction is safe and secure at this point. And then over the next 5 minutes, an hour, depending on your settings, the background process will start updating the data files. So the actual data tables in Postgres, they don't get updated till a little bit later. And they happen generally as a background activity that keeps happening. So every single piece of data gets written at least twice. And in many other cases, it gets written many times because what I'm not including in here is when a tuple gets created and updated, all the indexes that refer to this data may need to be updated. If an index is referring to one of the columns that was changed by this tuple, then that index needs to be updated. If the tuple changed location, then the index again has to point to the correct place. So there can be a lot of writing data to a database is very expensive, and it is only considered safe when it makes it all the way to the disk layer. For reading, if we go back for a second, you want to grab it from the cheapest place you can. So the earliest cache, the closest cache to where you're processing, if it has the right data, you know it's good. You just grab it and you read it. You don't need to go. You want to avoid going to the disk if at all possible. Disk is slow. For writing, you only consider the transaction to be committed safely if it made it to the disk on some level, which means that in an ideal world, you want to keep all of your I/O for the writes. If you have a given amount of disk I/O, you want to have as much of it available for your write activity because that's the one you cannot avoid going to disk. All right, so now we're finally going to talk about parameters. So what I find as the perfect parameters that are important for performance? So shared buffers, we talked about it briefly. It's the main area of Postgres that the database as a whole is keeping track of all its what I usually call a work set. So the subset of database that is actively being worked on. Work mem, which is per connection memory. Max connections. This is not a parameter that is usually included in performance, but I think it's actually very important, and we'll go a bit more in depth on that. And then effective cache size, which really it's a guideline of how much memory you've got available for the file cache. Now, we're also going to include a couple of bonus parameters, which is they're not really part of the stock, but they're important enough where it's worthwhile to include them, which is we're going to talk a little bit about the vacuum and the maintenance tasks, the random page cost, which is in my mind a bit of a legacy parameter that was set for a old style hard drives, and it's still set like that for a default. So it's worth mentioning. And then a few other trade-offs. So shared buffers. So it is a section of memory that is allocated to the main process. It is used to cache table data. There's actually structure inside of that. There are different pieces that are used. There is like a ring buffer if you need to read data serially, but for the most part, we can just ignore all of that and say that it is the amount of memory that is used for Postgres to cache the database so that it doesn't need to go to disk. Why would you want to increase it? You want to in order to improve performance and to reduce the reading. You want to reduce the likelihood that you need to read from disk. How do you monitor it? So there are, in Postgres database, there is a number of pgstat.io tables. There's pgstat.io user tables. And this is a calculation you might want to do. So for each table, Postgres keeps track of how many blocks, heap blocks were hit versus how many were read. So hit, it was hit in a, basically it was able to find it in a cache, and then read, it had to read them from disk. So by calculating the percentage, you're able to tell on a per table basis whether it's accessing the table was able to be satisfied on average from its cache versus it had to go to disk. Sorry, that's not exactly accurate. Postgres doesn't know whether it was able to get the data from the file cache or from the disk. That is all done transparently at the OS level. So the heap blocks read is really, it had to get it from the OS. What's the good starting point for shared buffers? It's about 25 to 40% of the total RAM of your server. That's generally considered a good starting point. There are some reasons why you may want to go higher or lower. That would be dependent on your workload and how much data you're processing. If you have a very large database, but only, let's say, hypothetically speaking, you've got a database that spans back 7 years, but most queries are only looking at the last 3 days worth of activity, and only rarely you have a reporting query that looks for a week or more. Then you can actually probably reduce your total RAM because you just might not need it. But you do that by checking the pgstat.io user tables, for example. Workmem. So this is memory that can be allocated to each connection. It is a bit of a misnomer because on a modern Postgres, it can actually go double the amount. The typical, I think, usual default starting point is something like 4 megabytes, I think. But it's common to have like 30 megabytes, 60, depending on the amount of data that the query is expected to keep track of. Every time we do a sort, it goes a lot faster if it can be put in a memory versus sorting on disk. If you need to do joins, you need temporary storage space for the primary keys or to basically control your joins. So the more memory you can give to each connection, the more likely it can do its work almost entirely out of RAM, and life is good. Things go a lot faster. How would you? If you have more complex queries with more joins, you need more RAM. How would you check if you need to increase workmem? you'd use explain analyze on the queries that you're considering. It would have to be done on a per query or the most common queries, most frequently executed queries. If you want to look at the system as a whole, one way is to check if you're creating a lot of temp files. If your queries cannot fit in workmem, they will likely create temporary files to store the data. So just checking if your system is writing a lot of data to temp files is a good way to check if there's problems. And of course, if you're creating temp files, that means you are reading and writing from disk, which is taking away from your write activity, from your I/O that can be used for the database to keep its updates, write it updates to disk. So the default 4 megabytes is generally reasonable, and then you would grow it as you need it. With very large databases, can go much higher. It's something also where on a, let's say, data warehouse type workload, you might see it very large, let's say half a gigabyte, but you would limit the number of connections allowed. So max connections. So this controls how many connections Postgres will allow to execute at the same time. I like to include it in a performance discussion for a couple of reasons. One is, if we're executing many queries at the same time, each one of those queries will have, presumably, their own view of the database, the own set of data that it needs to work on. If you allow 1,000 queries that are executing at the same time, then potentially your shared buffers would have to be much larger, because each one of those 1,000 queries could have a different subset of data that it needs to work on. So your cache needs to be a lot larger. Managing the cache it doesn't come free either, although it happens at memory speed, so it's not generally a large consideration. The other aspect of it is, when you have 1,000 queries executing at the same time, how much CPU will each query have? Our usual kind of guideline is to not go much beyond 10 to 20 connections per core. Because if you think about it, if we have let's say if we have a 16 CPU machine, it's reasonably sized these days, and you have 10 connections per CPU, so that's 160 connections. 160 connections total. What happens is that for each second of execution, each one of those connections only has 1/10 of a second of CPU time. So that's not a lot of time. When you go to 20 connections per core, each one would have, 5 milliseconds of execution time. So unless the queries are able to complete in that time, it's going to probably be ejected, or most of the queries will be waiting for data to arrive, or will be waiting for other logs, for other queries to finish their work before they can continue. So what you end up is kind of like a gridlock. Either a query, you've got a lot more logs to manage, you've got a lot more data in a cache. The cache has to be larger because the query is waiting. Maybe it's loading its data. maybe 9 queries are loading their data into the cache. 1 query is executing. There may be logs if there's long-running transactions where queries get ejected. It becomes a lot more chaotic, a lot more things to manage. And at the end of the day, things are just waiting. Having fewer active queries can actually result in a faster connection, in just better throughput. Just because a query is able to grab its data, execute it, provide the results, and move on. Now, this is balanced a little bit, which is why we recommend 10 to 20 connections per core, because accessing data from disk is slow. So in general, what you can do is 9 queries are loading their data and 1 is executing. And that seems to be a reasonable kind of starting point for trade-offs. So effective cache size, that is just a guideline. I'm not going to do my pirate impression because it's horrible. But it's an estimate. It helps Postgres decide how likely is it that the kernel is going to have this data in its own cache as opposed to going to disk. If you want to encourage index usage and reduce sequential scans, you'd want to increase it, and that simply means that Postgres is going to look at it and say, well, the cache size is pretty large, so even if I don't have this index loaded in memory, it's probably in memory at the file system level just because the file cache is available. When deciding when you want to increase it or modify it is you want to look at the OS disk and IO metrics. So the goal is to smooth out any large spikes. If you see large number of IO transactions just spiking and then dropping down immediately, that generally means that something that's cache would help spread out that workload over a long period of time, because the system is able to either use the cache to read the data or use the cache to hold it before it's able to write it out. And the default advice for cache size is about half of the total file system of the total system RAM. I think that's probably too large for very large systems. Like if we're talking about more than 128 gigabytes of RAM, having 60 gigs of RAM for file cache seems too large. However, it would require some testing. So let's do some what ifs. So we described a little bit about the components, the big pieces of Postgres, and a lot of it is really focused on getting data to and from the disk, because at the end of the day, that's the entire function of the database. You give it data to store safely and then retrieve it when you need to. So what if shared buffers is large enough to fit nearly the entire database into RAM? Well, that's actually a really good position to be in. Your entire database can be read from memory. There is no need to go to disk other than maybe after a reboot. There's no need to go to disk for anything other than to write the data. So all of your I/O, all of your disk I/O is available for writes and for making sure that your WAR files get to disk as quickly as possible. Maybe you may need some I/O for temporary files, but in generally this kind of setup would be very, very fast, with a few potential caveats. In case you have like double buffering, where you've got an interaction between the file system cache and the Postgres shared buffers. We might go into that a little bit. So what if shared buffers is too small? That's option number 2. What if number 2? So what happens is that almost every read request, or large portion of the read requests, end up needing to get data either from the OS cache, file cache, which requires a system call, which is serialized at the kernel, but regardless, it's slower. And then a large portion of those would require going to disk. Disk is, I don't know what the current ratio is. But at least it's several thousand times slower than memory. So it'd be slow. What if work mem is too small? Well, if we don't have enough memory for a query to keep track of the data that it needs to be able to sort in memory, it'll have to use temporary files, which then generally on modern systems, in the old systems, we used to have separate file systems for temporary files for different table spaces. That's less common these days. So it generally hits the same disk. It takes away from the disk I/O available for wall files for updating the database. So a lot more activity happens on disk. Queries generally take longer to execute because they cannot perform work in memory, cannot do sorting. That means that they run longer. Logs are held for a longer period of time, which then interferes with other queries, and it kind of spirals that way. What if we have number of connections 200 times number of CPUs? So this is 10 times our guideline. I went into it briefly before, which is the same thing. You've got your shared cache now needs to store data related to 10 times more queries than need before. So it ideally would need to be larger, or your caches get evicted all the time. So a query will start, will load its data, then wait. By the time it gets to execute, half of its data may be evicted because different queries needed the space. During this time, this query may have open logs, which then interferes with other queries. It just becomes a gridlock. What if number 5? So this is an edge case. So I mentioned that workmem, under certain conditions, the connection can actually allocate double the size of the workmem. So that's generally what we use. So what if your workmem, 2 times the workmem times the number of connections plus shared buffers is greater than RAM, than your available RAM? So that whole equation, all it means is, what if the memory that we allocated to Postgres is larger than the memory of the system? So shared buffers plus max connections times workmem is larger than available RAM. On Linux, there is this wonderful feature called out-of-memory killer, and its function is to protect the operating system from a runaway process. In this case, there is out-of-memory killer, which you cannot really disable. You can tune it a little bit, but you cannot really disable it. In this case, the out-of-memory killer would decide that Postgres is the runaway process. It's requesting more memory than it's available, so it has to be killed in order to protect the service. Which, from the point of view of the operating system is the service. From the point of view of database, obviously we don't agree. So in this case, what likely happens, what almost always happens, is the database crashes. Under best conditions, it's going to be reloaded. Under most conditions, it will just crash and stay down until somebody brings it back up. So you obviously want to avoid this scenario, especially that given that scenario 5, that would generally happen when your system is at its busiest. That's when the OS would decide that it is asking for too much and needs to be killed. So we finished the main part of the kind of discussing about the trade-offs of different pieces of shared memory versus work mem versus number of connections. Let's go into the bonus round, which is vacuum. So there is a lot of talk generally about vacuum and optimizing vacuums, and it is a very important topic. So we're just going to include it briefly here. So there is a set of parameters that is used to guide maintenance tasks. I mentioned earlier in this talk that Postgres doesn't really change data. It creates a new version of a tuple when it gets modified, and it kind of overshadows the old version of the row, which is great. But what happens to the old version? Well, eventually it's cleaned up by a vacuum, usually an auto vacuum or a manual vacuum task. But it's one of its functions is to find those old versions of the rows that no transaction is going to reference, because each transaction kind of keeps track of which versions of rows it sees from the beginning of its start, from when it started, and it can only see those versions of the rows. So as long as there's a transaction that is open that could potentially reference a given version of the row, it cannot be cleaned up. Which also brings us back a little bit to the beginning when I said when I talked about sorry. That brings it back a little bit. If we have when we talked about workload, and we have a long-running transactions, like in a data warehouse, and trying to manage workloads that have a lot of quick updates and a lot of long-running queries at the same time. As long as that long-running transaction is executing, it could potentially see versions of the rows from, let's say, an hour ago. So Postgres will not be able to do any kind of a cleanup for these fast-running transactions until the oldest running transaction can no longer see that version of the row. So trying to balance these kinds of separate types of workload between fast updating transactions versus really long running ones is where we typically get into trouble, because Postgres just needs to keep so many different versions of different rows available when you're trying to support different workloads. One of my favorite sayings is, if you don't schedule your maintenance, maintenance will schedule itself. Postgres does have facilities where it'll identify when it's going to get into trouble, when the transactions are you're in danger of what's called a transaction wraparound. It will schedule a higher priority vacuum. Eventually, it'll schedule a vacuum to prevent wraparound, which cannot really be escaped. Again, this often happens when the system is at its busiest. So trying to defer vacuum maintenance can have the effect of basically reducing performance of your system while it's at its busiest, and in a way that cannot really be skipped. If you go to the PostgresConf website, we should probably include a link. You can actually look up some of the other talks, which should be all available online, I believe. Which go more into Postgres vacuum internals. Originally, this talk was given during PostgresConf, so I've got links to talks where if you want to follow up on some of these topics. All right, random page cost. This is a holdover from 20 years ago, where majority of databases were running on spinning Rust on hard drives with the spinning disks. On this on those types of file systems, there's a big difference between accessing data sequentially versus accessing random data pages. On modern SSDs, there is not much difference between asking for random disk logs versus asking them in a sequential manner. On the old spinning disks, you had to wait for the platter to go under your read-write head, and that would take milliseconds, or that would basically take time. So reading data sequentially was a lot faster. So this parameter is still by default set to random page cost, but if you're using SSDs or NVMEs, you generally should switch it to 1.1 or even 1, which basically means tells Postgres that there isn't much difference between accessing data sequentially versus accessing data randomly, which is true. Not changing it for NVMe means that Postgres is less likely to use indexes, and it'll have generally a negative effect on a lot of the optimizations, on some of the optimizations at least. Okay, other trade-offs. Indexes. So this is going outside of parameters again. Indexes are used to trade space for more. You trade disk space for more work during inserts and updates. They're great when they work. Sorry, that's not true. Their indexes are great. They're awesome. They make access to your data fast, but there are some trade-offs. Updating indexes is not free, which means that if you have a lot of indexes on a table, and I've seen tables where, let's say, a 100 gig table would have 300 gigabytes of indexes on them. That means that for every write to it, if you write 10 gigabytes of data into that table, you're really writing 4 times the amount of space on disk, just by pure numbers. So they work great for reads, but they can they can cause extra work during. They do cause extra work during writes. And then unused indexes are expensive because even if an index isn't used, it still has to be kept up to date. So having an index means that all writes need to be considered when they could update this data. And again, same PGConf from this year if you want to follow up on any of those talks to go more in depth about indexes. Connection pooling. So this is now going outside of the database. We talked about max connections. One way of reducing the amount of work that the database is trying to perform at the same time for each connection is to utilize connection pooling, which will create a reusable larger pool for your application to collect, to connect to keep to make requests of queries. It'll be kind of serialized and executed on a database, and then the results get returned. This also connection poolers generally reduce the overhead of frequent connection creation. Connecting on a database side, when you connect to it, then a new process gets spawned. The work mem needs to be allocated. Authentication needs to happen. Connection poolers are generally a lot more streamlined with respect to all of this activity, so that it's faster and they keep a persistent connection to the database, so that the work just happens without reallocating the work mem. However, you do need to be careful about connection lifetime. So work mem doesn't really get cleaned up until after the connection ends. Most connection poolers, they do have some facility of recycling connections, so that you don't have a connection that's live. Doesn't have to be in the same transaction, but it you don't have a connection that's going for days or weeks, because what will happen is, since work mem isn't cleaned up till after the connection exits, you can basically guarantee that each one of your connections will eventually end up using the maximum amount of memory it can allocate, and that's not necessarily most efficient use of your resources. If most of your queries only require a small fraction of the work mem and only a few reporting ones require a bigger one. Caching. So this is, again, we're going outside of a database. We're past the parameters, but the best work or the fastest work you can do is the one that you can avoid doing. So if you can cache your data, Redis, or just caching it inside of the application layer, if you don't need to ask the database for the newest version of the record, because it doesn't change that frequently, then that's probably a much better use of your resources. Asking the database to do anything is generally expensive. The query needs to be parsed, connection may need to be established, memory needs to be allocated, authentication process. You may need, then actually executing the query, you may need to begin a transaction. A lot of different things are happening. So if you can just have it in a little cache that has your most frequent data, then that's generally a lot faster. And then this caching is great for storing results of queries that change infrequently or on a schedule. So if you only update this table once a day, then you might actually cache it for a few hours and then just invalidate the cache when you need to, when you're expected to have new data. So, summary. We talked a little bit about how data moves through Postgres or through a database in general. It's all about the disk for me. The CPU, memory, and all of that is important to process the queries, but at the end of the day, the ratio of performance between memory and disk is generally skewed so heavily in the disk being slow that I usually start the optimization process just by looking at the disk and trying to figure out how to use it less. And best work is the work that you can avoid, which works for databases and also work. And the documentation is your friend. Everything that I described here, it's in the Postgres documentation. The pgstat.io tables, they're all very well described in what each value means and how you can query for it and how you can use it. It's well worth going through. Now, originally, this talk included a survey, so I just wanted to include the results from that, and we might actually throw it in at the end if anybody wants to fill out the survey to add to this graph. That would be kind of cool. So question number one that I had during the presentation was, what is the most common bottleneck? And I found it kind of interesting that, one, it's relatively even between CPU and disk. I didn't have too many results. And a lot of people just don't know. I would assume that either they don't know, or maybe it's locking or something of that nature. My initial thought was that disk would be much more prevalent, but it's not, which may be interesting. Maybe I'm wrong, or maybe a lot of times when a query is waiting for disk, it's just showing up as a log, or just showing up as waiting. It's not being executed. And what is the go-to response when faced with a performance problem? Again, it's far more even than I expected. Adding a read replica is the tail of this, which I guess it makes sense because that's a lot of extra resources that you're trying to add, and potentially a lot of complexity. I can understand why optimizing queries isn't higher, although I would say that's probably the best return on investment. The problem with optimizing queries is when you have an incident and you've got a database that is slow, this step generally takes days in order to for non-trivial queries, you need to write the new queries, you need to test them, deploy them to the application, update the application, deploy the new application cluster if that's what you're using. So in a real world, optimizing queries, it often comes with a long time before it can actually be deployed. You generally want something much quicker to take the pain away. And this is where the top, the first four get used more often. So adding an extra index, tune parameters, that's all instant, often without a restart, or even increasing the machine size is a viable kind of first step response, often with a promise to eventually optimize the queries, which may or may not take a while. All right, so that concludes the presentation. Are there any questions? Oh, the slides are available on the PGConf website, so we can definitely drop a link for that. So to reply to Bill, hi Bill. So is the question is, isn't workmem affected by max connection? Or am I thinking? Yes, they're related. So for each connection, each connection can request up to generally 2 times the amount of workmem. So if you allow more connections, you could potentially allow more memory to be allocated to all of the aggregate workmem. So yes, they're related in that sense.
Okay, thank you, Greg. I'm back. I'm gonna ping the next question right here.
So TempFS. Actually, Ildefonso responded to this one. Isn't TempFS virtual memory? So TempFS is like a RAM disk. So I have run some tests for a different presentations when I run an entire database out of a RAM disk, and it is fast to be able to do that. But that's not really related here. Actually, I'm not sure what this question is asking.
I think it's probably relevant, or it was in the middle of the presentation, but Ildefonso answered right here, and the same with the next one. So I'm gonna jump to the next one.
Oh, okay, Sakumar, how can we ensure vacuum full is run automatically for a table, which usually has a lot of updates and deletes? You generally don't want to run a vacuum full automatically. Vacuum full will take an exclusive lock on the table. It'll basically, what it does is it creates a new copy of the table. It copies all the live data into the new table, and then substitutes it for the old one. It's a safe operation, but while this happens, it's nothing else can really do much on that table. So if it's a large table with many gigabytes of data, that can be a pretty serious event. So there are other processes you can do if you want to avoid a vacuum full, like using PG repack, for example. But I wouldn't generally trust running them automatically. There's too much potential for things going wrong, and you generally want to schedule these activities for low period when the system isn't that busy.
Okay, next one. I just pinned it here from Sukumar.
Okay, I think it's without a primary key. Yeah. I'm not actually sure about the answer to this one. It seems to be a conversation between Ildefonso and Sakumar. One option might be if you can contact me and I can see if I can research that for you. In general, you may want to have a primary key, or I need to understand like how large the table is and how the data is going in and out of this table. One possibility is generally to tune the outer vacuum to the point where you're less likely to require a repack or a vacuum full. That may include making sure that every data block has a little bit of extra space for updates, or just changing how the data is, how the table is loaded and updated. One thing that happens in when Postgres does what's called bulk updates. When you update a single row, Postgres will try to find a place where to put it, hopefully on the same data page, so life is good. But if you're performing an update that creates more tuples than a single data page, then Postgres will generally just create a new data page and put it at the end. It's more effective, more efficient than trying to find in a free space map where to put each one of those rows. I have a lot of new tuples to put in. It's more than one data page, so might as well just append a new data page at the end. It's efficient in a moment, but it does create bloat. So you may want to look in the process that performs the update to try to avoid doing bulk updates if at all possible. If you are reloading a table, because I see that pattern quite frequently, it's more effective to, let's say, truncate the table first, get it down to 0, and then load it again, than it is to do a delete and then a bulk update. Okay, so Shil, about connection pooling, and I apologize if I get your names wrong. I'm doing my best. So for connection pooling, do we have to have a memory CPU the same as other servers, like master slave, if connection pooling is running on the server? So connection pooling is generally lower resources. They don't store a lot of their own data, just whatever data is in flight, and they generally are much more efficient in both CPU and RAM. So those can be much smaller.
I think
Thank you.
that's all. First of all, thank you, Greg, for joining us today for such an insightful presentation. And thank you, everyone, for being part of this presentation. And we look forward to seeing you in the next webinars from the 2025 PostgresWorld Webinar Series.